So let us do some more problems on direct products and finitely generated Abelian groups before we complete this chapter. So the first problem we are going to attempt is whether these two groups Z12 times Z2 and Z4 Z6 are these isomorphic. That's what we are going to try. Both are finite Abelian groups of order 24. So this 12 we can write it as C4 times C3 because 4 and 3 are prime to each other. So we are going to use the result Zm n is isomorphic to Zm cross Zn when GCD of m comma n is equal to 1, meaning there is no common factor between m and n. So this we can write it like this, and we can write the C2 as it is. And here we are going to write Z4, and this we are going to write Z2 and C3 because of the same reason this is isomorphic to C6. So they are actually isomorphic. Only thing is this is definitely isomorphic to this. If you rearrange the components, it's exactly the same. So Z12 Z2 is isomorphic to Z4 Z6. Now let us do another problem. Let's say let P and Q are two distinct primes. And R is an integer greater than 0. Then let G1 and G2 are Abelian groups of order P to the power of R and Q to the power of R. Now what we do is let us compare the number of possible groups that are isomorphic to G1 and G2. So one of the ways we can express G1 and G2 are like this. G1 is isomorphic to CP times ZP times dash ZP R times. Because every finitely generated Abelian group, this is finitely generated because it's already a finite group. So finitely generated Abelian group can be expressed as something like this. We don't have the infinite component of we don't have infinite component of this group. We only have the the finite component. So G2 can be written as ZP CQ times CQ times dash 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 CQ R times. But this is not the only possible way of finding the isomorphic group of H1, G1 and G2. We can rearrange this one as P square times then again Cp times dash dash then Cp. This is probably R minus 2. Similarly here. So the number of ways G1 can be isomorphic is same as the number of ways G2 can be isomorphic. Meaning isomorphic to a group, doesn't matter. So the number of possible ways G1 and G2 are isomorphic. Isomorphic to a group or this does not mean that G1 is isomorphic to G2. All we are saying is the number of ways G1 could be isomorphic to a group of this form is same as the number of times G2 can be isomorphic to a form like this. Either this or the derived form like ZQ to the power of Q square, etc. So there are several ways of expressing like this and several ways of expressing like this. That number are same. Does not mean that G1 is isomorphic to G2. So let us do a problem using this result. Let us find out the number of possible Abelian groups up to isomorphism of order 100,000. So 100,000. So that means the order of G is 10 to the power of 5. We are going to use one more result here. If M and N are prime to each other, then the number of Abelian groups up to isomorphism is Rs, where R is the number of abelian groups with order M, and S is the abelian groups of order N. For example, if you take two different integers, for example, let us take 12 and 21, not 21, 35. These two are prime to each other, and the number of different abelian groups here, this is actually equal to 3 times 2 square, and this is equal to 5 times 7. So this can be written as, if the order of the finite abelian group is M, one way is writing is Z2 square, or C times C2 times Z3. Another way of writing is Z2 square times Z3, or this is 4, and that's all. So there are only two ways of writing. There are two ways of writing an abelian group of order 12. Here it is very straightforward. There is only one way of writing this. Then that is Z5 times Z7. So if there is a group of order Mn, and that is 35 times 12, this is 6, no, 3, 36 plus 6, 42. If you want to express abelian groups of order 420, then it will be this times this, that is actually 2 times 1, and there are only two ways. And that would be Z2 times Z2 times C3 times C5 times C7, and another one would be C4 times C3 times C5 times C7. So if M and N are prime to each other, and R is a number of ways that a group of order M can be isomorphic, and similarly S is the one. S is a number of ways a group of order N can be isomorphic. Then R is the total number of ways that a group of Mn can be isomorphic. So we are going to use this result. So we can write it like this. This is equal to 2 times 5, and that is 2 to the power of 5 times 5 to the power of 5. And these two are prime to each other. These two are prime to each other. So this is our M and this is our N. So we need to find out how many ways 2 to the power of N can be expressed. So a group of order 2 to the power of is isomorphic to one of the following direct products of cyclic groups. And what are they? That is, we can write it as Z, Z2, 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 Z2. And second one will be Z2, 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 Z4. Third will be Z2, Z2, Z8. Fourth will be Z2, Z16. And fifth will be Z32. And sixth will be Z4 times Z8. Third will be Z2 times C4 times C4. So these are the only 7 ways 2 to the power of 5 and a group of an Abelian group of 2 to the power of can be isomorphic to. So similarly, an Abelian group of order 5 to the power of 5 will be isomorphic to one of the 7 direct product of cyclic group. So this 7 direct products will be exactly like this by replacing 2 by 5, 5 by 4 by 25, etc. Exactly like this. And when you combine this result, because 2 to the power of 5 and 5 to the power of 5 are primes, and there are 7 ways of expressing this and 7 ways of expressing this. So the total number of direct product of cyclic groups that an Abelian group of order 100,000 10 to the power of 5 can be isomorphic is 7 times 7, 49 times. So there are 49 ways in order of Abelian group of order 10 to the power of can be isomorphic. Now let us take an example of an Abelian group of order 72. So this can be written as, so this is 72 is equal to 2 cube times 3 square. So this group will be isomorphic to one of the following. One is C2, 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 C3, Z3. Second one will be C2, Z2, Z2, Z9. Third one will be Z2, Z4, Z9. Fourth one will be Z8, Z9. fifth one will be Z2, Z4, Z3, Z3. And the sixth one will be Z2, Z8, Z2, Z3 times. These are the only 6 ways an abelian group of order 72 can be isomorphic. One of these. But in here, see, there is a cyclic group of order 72, and that is 0 dash at 71, Z72. And that is actually isomorphic to this. And none of the other 5 ways, they are not cyclic. Because they are not cyclic because here you have a Z2, Z2, which is not cyclic. Here you have Z2, Z2 as a subgroup. Here also you have Z2, Z2. This Z2 is a subgroup of this. So if you take just the Z2 part of this, then this will be isomorphic. There is a subgroup isomorphic to this. And here also Z3, Z3. And here again C3, C3. So we can easily say that an abelian group is not cyclic if it contains a subgroup of this form. And that's what we are going to write it here. Result. A group, an abelian group, is not cyclic if it contains a subgroup of the form ZP times CP for some prime P. So let us try to prove this. So let the abelian group has a subgroup isomorphic to ZP, ZP. Then what happens? ZP times ZP is not cyclic. Sure, there is no problem about it. And every subgroup of a cyclic group is cyclic. And that implies the group is not cyclic. So what we have done here is the abelian group has a subgroup of the form ZP cross ZP. Then we proved that it is not cyclic. Now we are going to assume that the group is not cyclic and show that it has a subgroup of this form. So assume that the abelian group has a abelian group is not cyclic. Abelian group is not cyclic. And that implies the group has a subgroup of the form ZPR, ZPS for same prime P and integers R comma S greater than 0. This is true because otherwise the Abelian group will be cyclic. If an Abelian group is just of this form, just P or P times PR times P ZS, these are all primes, then it is cyclic. So one of them should have more than one power of P or R or S, and that is what we are saying here. If it is not cyclic, there exists at least one subgroup of this one. Now, the subgroup generated by PR minus 1 and subgroup generated by PS minus 1 are subgroups of ZPR, ZPR and ZPS, and that implies PR minus 1, the subgroup generated by PR minus 1 times S minus 1 is a subgroup of CPR, CPS and is isomorphic to ZP, ZP. And that concludes the result. Now let us define a special kind of groups. A group is decomposable if it can be expressed as a direct product of two or more non-trivial subgroups. See, I am not mentioning it is a Abelian group. It is any group that can be expressed as a direct product of two or more non-trivial subgroup. It is called decomposable. Otherwise, it is indecomposable. That means if we cannot express as a direct product of two or more non-trivial subgroups, it is indecomposable. Now let G be a finite Abelian group. Then, using fundamental theorem, this group is isomorphic to direct product of cyclic groups. Okay? If G is indecomposable, there is only one component in the direct product. That is, if G is indecomposable, if it is indecomposable, then G is isomorphic to CPR for some prime P and integer R greater than 0. So then CPR is always indecomposable. Because if ZPR is equal to ZPI cross ZPJ, where I plus J is equal to R, then the order of every element in ZPR, ZPI, ZPJ is P to the power of maximum of Ij. But ZPR is a cyclic group generated by 1 with order P to the power of R. So that means ZPR is always decomposable. It cannot be decomposed like this. So that means every finite indecomposable Abelian group is cyclic of prime power order. If you take any finite indecomposable Abelian group, it's always going to be a cyclic group with a prime power order. So it's be always like ZPR. Let us go back to our old Lagrange's theorem. If G is any group and H a subgroup of G, then order of H divides order of G. But we found a counterexample that if there is a divisor of the order of G, we don't necessarily have a subgroup with that order. Meaning, in the case of alternating group with the 4 elements, that is A4, the order of A4 is equal to 12, and 6 divides 12, but there is no subgroup of order 6 of A4. This is a counterexample and this is a Lagrange's theorem. But in the case of finite abelian group, let G be a finite abelian group and if M divides the order of the group, then G has a subgroup of order M. See, in this case, it is A4 is not an abelian group. Here, this is in a finite abelian group. If it's a finite abelian group, the converse of Lagrange's theorem is true. So, G is a finite abelian group implies G is isomorphic to ZP1R1, ZP2R2, ZPnRn, where the order of G is equal to P1R1 times P2R2 times dash dash Pnr. So M divides the order of G implies M is equal to P1 to the power of R1 or P1 to the power of S1 times P to the power of S2 times dash dash Pn to the power of Sn for some Si's less than or equal to array. It could be zeros also. Some of the Si's are zeros also. So this implies P to the power of P1 to the power of R1 minus 1 times P to R1 minus S1, P to the power of R2 minus S2 dash 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 P n Rn minus Sn is a subgroup of G of order P to the power of P1 to the power of S1 times P2 to the power of S2 times dash dash Pn to the power of Sn, and that is equal to M. So that means G has a subgroup of order M. So we are going to complete this chapter on direct product and finitely generated abelian groups with our last problem. If M is a square free square free integer, then any finite Abelian group of order M is cyclic. Square free means there is no factor of M that is a square. For example, 12 is not square free because 4 is a factor of 12. 4 divides 12 and 4 is a square. So let G be a finite Abelian group of order M. Then by fundamental theorem on Abelian groups, finitely generated Abelian group, G is isomorphic to ZP1R1 that CPNRN. It is finite, but because there is no components after this. But it is square free, and we can say that where M is equal to P1R1 times that as PNRN. Since M is square free, R1 equal to R2 equal to that as Rn is equal to 1. And that implies G is equal to CP1 ZP2 that is ZPN, where P1 that is PN are distinct primes. When I say distinct primes, the theorem does not say that it is distinct, but because M is a square free integer, it has to be distinct. And that implies G is cyclic.